I want to evaluate a double integral using polar coordinates. If you notice right now, the limits of integration suggest that this is the top half of a circle of radius 5 because y equals the square root of 25 minus x squared is just half of x squared plus y squared equals 25. We have a couple of problems here. One is that's a very difficult region to integrate over, and secondly, my integrand actually can't be integrated because of that 3/2 power. So if we decide we're going to switch this over to polar coordinates, then when I look at this region and I say let's consider what a sector looks like, the radius of the sector is going to go from 0 to the outer limit, which is 5, and the angle of the sector will range from 0 to pi. So we notice that r will be between 0 and 5, theta 0 and pi. So when we switch this over to polar coordinates, right here we have r squared raised to the 3/2 power times r integrated dr d theta. This extra term here we derived in the first part of this video. Now the limits of integration will be 0 to 5 in r, 0 to pi in theta. Notice we have constant limits of integration, which should make this much, much simpler. So r squared to the 3/2 times r will simply be r to the 4th power. When I integrate this, I'll get 0 to pi, 1/5 r to the 5th, 0 to 5 d theta. 5 to the 5th power times a 5th would be 625 d theta. So the constant integrated theta will just be the constant times the difference in the limits, or 625 pi. Notice the integration itself was rather simple when we switched over to polar coordinates. This is typically going to be the scenario when your region is either circular in nature or your integrand suggests that switching over will be easy because x squared plus y squared is r squared. Now let's try another one. Okay. Let's find the volume bounded by f of xy equals 36 minus x squared minus y squared and the xy plane. So right here you'll notice that we have a circular paraboloid which is opening downwards. So if I were to draw the picture of that, it would look something like this. And the intersection in the xy plane is simply a circle. Now, which circle is it? Well, if I'm bounded by the xy plane is z equals 0. So if I'm trying to figure out what that circle looks like, I'll simply replace z with 0. And you'll notice we get x squared plus y squared equals 36, which is a circle of radius 6. I would like to set up this integration using polar coordinates because it'll be much simpler. I have a circular region and my integrand is this. So if I'm setting up the volume problem, I can go directly to the xy plane first. It'll be the top minus the bottom. So z equals this minus z equals 0. But because we know we have a circular region in general, that makes for a very difficult integration. So if I switch this to polar coordinates instead, we notice that r is going to range from here. We'll see that r is going to range from 0 to 6, because it's a circle of radius 6. I'm going all the way around, so theta will range from 0 to 2 pi. So in polar, this integral will be 36 minus, that's subtracting that sum, so this is 36 minus r squared, r dr d theta. My limits of integration will be 0 to 6 in r, 0 to 2 pi and theta. Okay? I'll distribute first. And we'll have 36r minus r cubed dr d theta. Now I'm going to erase the top part so I can finish the integral. So if I integrate this with respect to r, then we will get 18r squared minus 1/4 r to the 4th from 0 to 6 d theta. So simply evaluating that at 6, we find that is equal to 324 d theta. Again, a constant integrand. I just simply multiply it by the difference in the limits, and that will be 648 pi. Again, a fairly simple integral if I do this conversion. So you would switch to polar whenever you have, again, a circular region in general, or an integrand where you see x squared plus y squareds, perhaps raised to different powers. You don't have to switch to polar, but in the event that you do, it usually is going to make the problem much easier.